Yeah, good afternoon, students. Good afternoon, JNV Ramnagar students. Am I visible and audible? Hello, are you there? Can you able to see my screen? Just let me know in the chat box. Yes, okay. Okay, fine. So let's start with the today's class. Today we are going to start a new chapter called the equilibrium. And in today's part, we will discuss the chemical equilibrium. And then the next session or in the upcoming sessions, we will discuss the ionic equilibrium. Okay. So under chemical equilibrium, the learning objectives for today's session is what is equilibrium and then what is chemical equilibrium, and we are going to study the characteristics of chemical equilibrium, types of it, and law of mass action, law of chemical equilibrium, types, properties, and applications of equilibrium constant, and at last we are going to discuss the Le-Chatelier's principle. Okay, so let's start with the definition of equilibrium. So what is an equilibrium? Equilibrium represents the state of a process in which the properties like temperature, pressure, or concentration of a system do not show any change with the passage of time. So, at equilibrium, the two opposing process takes place at an equal rate. The rate of forward reaction, the rate of reverse reaction, they will be equal. Okay, so nothing can alter it. Okay, even after as times pass by, so the change in temperature or pressure will not affect it. So that state is called as equilibrium state of that particular system. Okay, now coming to the chemical equilibrium. So let us consider a reaction. Okay, so we are considering a general reversible reaction which is occurring in a closed vessel. So A and B are the reactants and C and D are the products. So A and B giving C and D. So the rate of that particular reaction, forward reaction, is represented by RF, and for the backward reaction, it is represented by RB. Now at equilibrium state, as I have already told you, the rate of forward reaction will be equal to the rate of reverse reaction or backward reaction. RF is equal to RB. So let me show you an example. So here in this GIF, you can see that nitrogen is reacting with 3 moles of hydrogen to give 2 moles of ammonia. Okay. So nitrogen and hydrogen are the reactants. So they combine to give ammonia. Now ammonia is breaking down to give nitrogen and hydrogen. So here you can see, I think. So the green color balls are nitrogen and this pink color is hydrogen. Now they are coming and forming ammonia molecule. 2 moles of ammonia is being formed, and again ammonia is breaking down to give the nitrogen and hydrogen back. Okay, you can see that, right? Now these two components, reactants and products, they are in equilibrium with each other in this GIF, you can see. I hope you can understand this. Is this clear for all? Jain Viramnagar, is this clear to all of you? Those who are watching, any doubt from this? Okay. Yeah. The reactants will be in equilibrium with the product. So as the time increases, so this is the concentration of the reactant. Okay, A plus B. Okay, this is the concentration of the reactant, and this is the rate of the reactant. Now for forward reaction, A plus B will give C plus D, and at one point equilibrium is achieved. There is no change. Okay, even if you increase the time, there is no change in the concentration of A and B. The same way for reverse reaction also, product will ammonia will give nitrogen, hydrogen, right? That C plus D will give A plus B. That is for reverse reaction. At one point, both of them are attaining the equilibrium point. So this is the graph which represents the both the reactions. Okay. Now let us discuss the characteristics of chemical equilibrium. The very first characteristic is the chemical equilibrium is possible only in closed system, not in open system. It is possible only in closed system, and it is dynamic in nature. It is not static. It will always be moving. It is dynamic in nature, and the properties like temperature, pressure, color, and concentration, if you see, they remain constant. They will not change for chemical equilibrium system. And it can be achieved from both the sides. A plus B giving C, and here A is giving B plus C. Okay. So it can be achieved from both the sides. Reactant will give product and the product will give the reactant. You can see here. Okay. It can be achieved from both the sides. And next is the types of chemical equilibrium. Types of chemical equilibrium. Okay. So there are two types of equilibrium. One is homogeneous equilibrium or homogeneous equilibrium, and the other one is heterogeneous equilibrium. So now what is a homogeneous equilibrium? So when all the reactants and products are in the same phase, then we call those reactions as homogeneous equilibrium system. For example, when nitrogen reacts with this hydrogen, here you see the phase of the reactant and the product, they are same. All of them are in gaseous phase. So it is an example for homogeneous equilibrium. So in the same way, here also everything is in the aqueous phase, and this Fe3 plus is also present in its aqueous form only. So here again is an example for homogeneous equilibrium. Now what is heterogeneous equilibrium? Just the opposite of reactants and products are in more than one phase, then we call those reactions as heterogeneous equilibrium reactions. For example, so the liquid water is getting converted to vapor, gaseous system. Okay, so it is an example for heterogeneous, and here solid, liquid, and aqueous form of the calcium and hydroxide. So the phases are different. One is in solid and the other one is liquid and the other one is aqueous. So it is in more than one phase. The reaction is in more than one phase. So it is an example for heterogeneous equilibrium. So is this clear for all till this? The characteristics and the types, definition. So everything what we have discussed so far is clear to all. Shall we move on to the next part? All the things are very easy only, just the basics. Shall I move on to the next topic? Yeah. The next is law of mass action. So what is law of mass action? For any reaction, if you take, the rate of the reaction will be directly proportional to the active mass of the reactants. Active mass of the reactants. Now, what is this active mass? What is meant by active mass? It is the mass of the substance participating in a chemical reaction. Mass of the substance participating in a chemical reaction. Okay. Now, solution, the active mass is represented by the molar concentration. If you are having gases as the reactant, then we have to represent it by partial pressure. If we are having a pure solid as a reactant, then the active mass is constant. That is, it is equal to 1. And for pure liquid also, the active mass is equal to 1. Okay, for solution concentration, for gases pressure, pure solid and liquid, the active mass will be equal to 1. Okay, so it depends on the rate of the reaction. Rate means speed, right? The speed of the reaction depends on the active mass of the reactants which we are having in our reaction. Now coming to the law of chemical equilibrium. Law of chemical equilibrium. So let me take two expressions. One is the rate of the forward reaction, the other one is the rate of the backward reaction. Suppose if I am having AA plus BB giving CC and DD for this reaction. So this is the rate of forward and this is the rate of the backward reaction, right? So if I write RF, then it will be equal to the rate of the reactant, concentration of the reactant raised to the stoichiometric coefficient. Okay, so that is giving this expression. And for the backward reaction, C and D are the reactants, right? So the rate depends on the concentration of C and D. And the small C and D represents the stoichiometric coefficients. That's what we are keeping that in power. Okay, so the rate is proportional to the concentration of the reactants. Okay, and what is this Kf? It is the rate constant. Kf is nothing but the rate constant. And for to write the equilibrium constant, which is called as Keq, the expression should be like this: Kf by Kb is equal to Keq. Now, if we substitute the term Cc and Cd and A and B, and this reaction, this expression is nothing but the law of chemical equilibrium. This is the law of chemical equilibrium. It is equal to the product of the product concentration divided by the product of the reactants concentration raised to their stoichiometric coefficient. So if you are given any reaction like this, if I am given A plus B giving C, then for this reaction, if I want to write Keq, then I have to keep the product first. So C is the product divided by A and B are the reactants. Okay, product by reactant concentration will give us Keq. Keq is called as equilibrium constant. And this whole expression is called as law of chemical equilibrium. Okay. Now, if we have to see the unit of this Keq, the unit of Keq. So, in each thing we are having the concentration term. Concentration is nothing but number of moles by concentration is equal to number of moles by volume. So, for the number of moles, the unit is mole, and for volume, it is liter, right? So, it is nothing but for concentration, the unit of concentration is mole per liter. So, if we substitute the unit in all the cases, we are getting this type of expression where mole per liter is raised to C plus D minus A plus B. Okay, unit of Keq. So now this Keq. So any doubt from the Keq part for anyone? This is very important. Calculation based on this equilibrium constant will be asked. Okay, in all the numericals. This is very, very important. Very easy. Just you have to write the product by reactant. If you're having any stoichiometric coefficient here, 3C, A, B like this, then you have to put that in power. That's it. Okay. Nothing to do much here. Okay. Shall we move on to the next topic? Types of equilibrium constant we will see. Types of this Keq we will discuss. Shall I move on to the next slide, students? Okay. The types. Types of Keq. The equilibrium constant Keq has two types. One is in terms of molar concentration. If it is in terms of molar concentration, then we have to call this Keq as Kc. The second is in terms of partial pressure. So it is previous slide. Okay. Just let me know once you are done with it, okay? The C denotes the concentration. It can be the concentration of C or concentration of D, concentration of A or B. Okay, finished? Yeah. Coming to the types of equilibrium constant, we have two types as I have already told you. It is molar concentration, Kc, and in terms of pressure, it is called as partial pressure, Kp. Now for the reaction AA plus Bb giving Cc and Dd, if I have to write Kc, what I have to do? Concentration of C raised to the stoichiometric coefficient C into concentration of D raised to the stoichiometric coefficient, that is D, and for A and B also the same thing. So this capital C denotes the concentration. Capital C denotes the concentration. If I have to write the Kp for the same reaction, if I want to write the Kp for the same reaction, instead of this concentration, you put partial pressure. Partial pressure, that's all. So the C denotes the concentration. C denotes the concentration here, and the P denotes the partial pressure. It is partial pressure. Okay. So that's all. Product by reactant raised to their stoichiometric coefficient. That's all about this equilibrium constant. Okay. Now we will see the relationship between Kp and Kc. So there is one very important relation which relates this Kp and Kc, and it is given to you on the screen. Kp is equal to Kc into RT power delta Ng. And for Kc, Kc is expressed by the unit mole per liter to the power delta Ng, and for partial pressure, it is atmospheric pressure power delta Ng. Okay. So this is the relationship between Kp and Kc, which is very, very important. So from this, we are going to deal three cases. Case one is when this delta Ng goes to 0. When this delta Ng is equal to 0, what is the relationship between Kp and Kc? So if it goes to 0, we will put 0 in the place of delta Ng. So anything to the power 0 becomes 1, right? Anything to the power 0 becomes 1. So in this case, Kp will be equal to Kc. So the example which shows this relation is here. So here delta Ng is nothing but the number of moles of gaseous product minus number of moles of gaseous reactants, right? So the number of moles of gaseous product is 2, and the number of moles of gaseous reactant 1 plus 1. It is also 2. So 2 minus 2 is 0. So if it is equal to 0, RT power 0 we will have, and Kp is equal to Kc. In the same way for this reaction also. H2 plus I2 giving 2Hi. So we should be very careful. All the things should be in gas phase. Then only we can substitute. Okay. And Kc and Kp are unitless in this case. There is no unit. For Kp and Kc, for delta Ng is equal to 0 case. Clear? Then we'll move on to case 2. When delta Ng is positive, when delta Ng is positive, we have Kp equal to Kc into RT power delta Ng, and that is some positive value. Suppose, let me take 2 or 3, I can take. So if I multiply this Kc into that particular number, I will get Kp. Okay, so Kp will be greater than Kc. Kp will be greater than Kc. So see here, the product side we have 1 plus 1, 2 mole. So delta Ng is equal to, the product is having 2 mole, the reactant 1 mole, so it is positive. We are having 1, so it is greater than 0. It is a positive value. So for Kc, mole per liter is the unit, and for Kp, atmospheric pressure is the unit. Okay. And for the second reaction, we have 4 moles of product and 2 moles of reactant. So delta Ng will be equal to 4 minus 2, it will be equal to 2. So in this case, what we have to do? Kc is having mole square per liter square as the unit. And for Kp, it is atmospheric pressure, the whole square. And if it is 3, substitute 3. If you're getting 4 as the value for delta Ng, substitute accordingly. Okay. So this is how we have to get the units. Then for the third case, when delta Ng is equal to negative, Kp will be less than Kc. In that case, everything will go in inverse. So Kc will have a mole per mole power minus 2 and liter square. So everything will be inversed. Okay. So these are the 3 cases. All the 3 cases are very, very, very important. Now next we will discuss the properties of equilibrium constant. So the first property about this Keq is it is reaction specific. It is specific for a particular reaction. It is not common. Okay, it is specific. And for a given reaction, the KEQ depends on temperature. So the equilibrium constant depends on the temperature. Okay, and the third property says that for a reaction A plus B giving C plus D, it can be written like the product of product concentration by the product of reactant concentration. If this reaction is reversed, if I reverse this reaction, like C plus D giving A plus B, if I reverse this reaction, then the equilibrium constant can be represented by K dash. It is represented by K dash, and here for this reaction, A and B are the product and C and D are the reactant, right? Now, what is the relationship between this K and K dash? K dash is equal to 1 by K, reciprocal. It is just the inverse. If you are reversing the reaction, then you have to inverse the equilibrium constant. Okay, very important relation which we have to keep in mind. Then coming to the fourth property, for the same A plus B giving C plus D reaction, K will be like this. And if this is multiplied by the number n, if the reaction is multiplied by the number n, like if I'm multiplying by 2 or if I'm multiplying by the number n, the whole reaction is multiplied. Then the K dash will be concentration of product and reactant raised to the stoichiometric coefficient n, right? If I'm multiplying by a number, then the equilibrium constant K dash will be equal to K power n. It is K power n. So the multiplied number should be put it in should be in power. Should be denoted in by giving the power. Okay. And coming to the fifth property, if A is giving C and if B is giving D, okay, B and D are in equilibrium, A and C are in equilibrium. For A and C, if I want to write the equilibrium constant, let me take it as K1. The product is C, so the concentration of C divided by the concentration of A. So I'm taking this as equation 1. And for B giving D, it is D by B, right? If we add these two equations, if I'm adding two equations, if we add both the equation, we will get A plus B giving C plus D, right? Then K dash can be written like this. C by A is nothing but K1 and D by B is nothing but K2. So if I want to add both the equation, then I have to multiply the equilibrium constant of both the equation. Okay, what was the first thing? If I'm reversing the equation, I have to take the inverse. If I'm reversing the equation, I have to take the inverse. And if I'm multiplying by the number n, then I have to put that number to the power of that constant which is given in the question. Or if I'm adding two equations, I have to multiply the equilibrium constant. So these three concepts are very, 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 very important. Okay, regarding this equilibrium constant. Now, there is one very important application we have for this equilibrium constant. That is, we can able to calculate the standard Gibbs free energy, delta GR naught from KEQ. Okay, so if a reactant is in equilibrium with the product, then the delta GR naught can be calculated using this formula, which is minus 2.303 into RT log of KEQ. If this KEQ is greater than 1, if it is greater than 1, then delta G will be less than 0. So in the last class, when we were discussing about the thermodynamics lesson, in that thermodynamics I have told you delta G value should be less than 0 or it should be negative. Only then the reaction is spontaneous. So here it is less than 0. So this denotes that the process is spontaneous. This denotes that the process is spontaneous. So it will go in forward direction. Reaction will go in forward direction. Like R will give P, reactant will give the product. If KEQ is less than 1, then obviously delta G will be greater than 0. In that case, delta G will be having the positive value. If it is having positive value, then the reaction is non-spontaneous in nature. If it is non-spontaneous, then backward reaction has to occur, backward direction. Okay. If it is equal to 1, if KEQ is equal to 1, then delta G will also be equal to 0. Delta G will be equal to 0. If it is equal to 0, what does this indicates? This indicates that the reaction is in equilibrium. Reaction is in equilibrium and there is no shift in any direction. No shift in any direction. Okay, they are in equilibrium. The rate of both forward and backward, they are in occurring at the same rate. So there is no shift from reactant to product or product to reactant. Okay, this is the application of equilibrium. Many applications are there. This is one of the very important applications you need to know. Now coming to the last topic of this lesson, not this lesson, for today's class, it is Le-Chatelet's principle. So what is this principle? According to this principle, if a system in equilibrium is subjected to a change of concentration or change of pressure or change of temperature, then the equilibrium is shifted in such a way to nullify the effect of change. So what is happening? There is a reaction. That reaction is at equilibrium. Now, for example, you take this picture. We have A plus B giving C plus D. And here what I'm doing, I'm increasing the concentration of this C and D. I'm increasing, you see here, I'm increasing the concentration of this C and D. So in this case, what happens? The reaction will try to keep them in equilibrium by nullifying the increase that has happened in one side. So how does it nullify? By shifting the C and D to A and B side. That means the reaction will go in backward direction and it will nullify that effect. Clear? So one of the D has gone to this AB side and at last we got 2A and 2B and here 2C and 2D. Okay, now it has attained the equilibrium state. Clear? So here I am increasing the concentration. Like concentration, we can increase the pressure also. If I am increasing the pressure one side, automatically the reaction will shift in the other direction. Likewise, if I increase the temperature, the same thing happens. So whatever might be the change we are doing to that reaction, the reaction will try to keep themselves in equilibrium by nullifying the effect by shifting to either one of the direction. So this principle is called as Le-Chatelet's principle. Okay. Now we will see one by one. So first we will see the change in concentration. So for this, I have taken N2 plus 3H2 giving 2NH3 as an example. Now, if I increase the concentration of this reactant, okay, for forward reaction, these two are the reactant. And for the reverse reaction, NH3 is a reactant. Okay. So if I increase the concentration of the reactant, then the equilibrium will shift in forward direction. So if for my example, if I take this as reactant and this as product, okay, now if I increase the concentration of this nitrogen, I'm going to increase the concentration of this nitrogen. So what happens? Automatically, it will shift towards the product side. So forward direction. Equilibrium will shift towards the forward direction. If I'm increasing the concentration of this product, I'm increasing the concentration of this NH3, what happens? It will go to the reverse direction. Then only they can nullify the increase. Got it? So these are very important points which you have to keep in mind. Clear? So this is about the concentration. Now coming to the change in pressure. So any doubt from the concentration, from the change in concentration for anyone? These are the things that affects this equilibrium. Factors affecting the equilibrium. So I can see two people, Bhaskar, Anandaram and Suresh. Something. You guys are from which JNB? Are you guys from JNB Ramnagar? So is this clear for both? Okay. Okay. Nellore. Oh, guys, why you have joined so late? It's already 3:36. No, we have class at 3, so try to join on time, okay? From tomorrow onwards, try to join on time. So we are discussing the chemical equilibrium lesson here. And no issues for today. And from tomorrow onwards, try to join on time. And now I am discussing with Le-Chatelet's principle. I have completed the types of equilibrium, properties of equilibrium and some characteristics of chemical equilibrium. So those things I was discussing in the previous slides, and now I'm at the end of this session. Okay, so after completing this topic, we will solve some questions based on the topics that I have discussed today. Okay, fine. So coming to this principle, the first factor is the change in concentration. The second factor is change in pressure. Now, when the pressure on the system is increased, what happens? The volume decreases, right? Because we know that pressure and volume, they are inversely proportional. If one is increasing, the other one will automatically decrease. That is, the total number of moles present per volume increases. So this is the container which has some system or gas. So this is the initial volume. This is the initial volume. Now, if I increase the pressure, if the external pressure is increased to the system, what happens? It will get compressed. The gas will get compressed, right? The gas will get compressed. And now this is the final volume V2. Now I have applied pressure on this. This is the final volume V2. So what is happening here? The number of moles per unit volume. So here this is the space, and for the second system, this is the space. The number of moles, the number of atoms or the number of molecules or the number of moles present per volume, what happens? It increases. Since the space is getting reduced, the particle number is increasing. So this is the concept. Now if I increase the pressure, the equilibrium will shift to the direction in which the lesser number of gaseous molecules are there. If I decrease the pressure, if I release the pressure, then it will go to the side in which the greater number of gaseous molecules are there. Okay, greater number of gaseous molecules are there. Suppose if I'm having N2 plus 3H2 giving 2NH3, here all the three molecules are gases. All the three are gases. So how many number of moles we have in the product side? Only 2. But in case of the reactant, we have totally 4. N value is 4 and here N value is 2. Okay. So if I increase the pressure of the system, the equilibrium will shift towards the lesser number of gaseous molecules. If I increase the pressure in the reactant side, it will go towards the forward direction. If I decrease the pressure, it will go to the greater number of moles. Okay, so this is the concept for pressure. Now coming to the change in temperature, so the effect of temperature depends upon the reaction, whether it is exothermic or endothermic. So what is exothermic? If the energy is released, then we call those reactions as exothermic reactions. And if the energy is getting absorbed by the system, then we call those reactions as endothermic reaction. If I increase the temperature of an endothermic system, okay, that is if the system is absorbing heat and I'm keeping on increasing the temperature, means the system will keep on absorbing the heat, right? The system will keep on absorbing the heat. Then in that case, it shifts. The equilibrium will be shifted towards the forward direction. Suppose if I'm having A and A is giving B, okay, now this is an endothermic reaction. This process is endothermic. A is keeping on absorbing the heat. Now, if I still increase the temperature of this A, what happens? A will try to shift the heat that I have given to it to B. Then only A and B can be in equilibrium with each other, right? Can you able to understand what I am saying? Yes? Yes or no? Okay, if you're having any doubt, just ask me, okay? So if I increase the temperature of the system A, it tries to shift or transfer its heat to B. Means it is equilibrium is moving towards the forward direction. Okay. And if the reaction is exothermic, exothermic means heat is released from the system. Heat is released and I am giving the heat to the system. In that case, it works with the reverse reaction. Okay, it works in the reverse direction. And the other case is with the next thing. If I decrease the temperature of the system, for endothermic reaction, reverse reaction is favored, and for exothermic reaction, forward reaction is favored. Okay, you just understand one part. The next will be the opposite of this. So this is about the change in temperature. And we have some more things also, like we have the addition of inert gas. So if I'm adding some inert gas to my system, to the reaction, it will not affect the equilibrium. There is no change, there is no effect on addition of inert gas to the equilibrium reaction. Okay, so those are some other factors which affects the equilibrium system. Now with this, we are going to move on to the previous year's questions of JEE and NEET. So let's start with the first. The Kp for the following reaction is 3 at 1000 Kelvin. What will be the value of Kc for the reaction at same temperature? So we know that Kp is equal to Kc into RT power delta Ng, right? So what is delta Ng for this reaction? Delta Ng is nothing but change in number of moles of gaseous product minus gaseous reactant. So here the gaseous products are carbon monoxide. So the number of moles of it is 2. And while seeing the reactant, only one of the reactant is in gaseous form, that is carbon dioxide. So we have to take that only. So it is minus 1. So 2 minus 1 is 1. So delta Ng is equal to 1. So substitute the value in place of delta Ng. And Kp is also given in the question, right? Kp is equal to 3, which is equal to Kc. And R value is also given here. It is 0.083 into temperature is also given. It is 1000 Kelvin. It is 1000 Kelvin. Our delta Ng value is 1. It is 1. So Kc will be equal to 3 divided by 0.083 into 1000, right? So what we will get? We will get 0.036, or I can shift 2 digit and write 3.6 into 10 power minus 2. Okay. So this is the value of Kc. This is the value of Kc, in which option C is the correct answer. The value of Kc for the same temperature is option C. Got it? So from the relationship between Kp and Kc, we are arriving at the answer for this question. So any doubt from this question? Shall I move on to the next question? Yes or no? Give me a thumbs up or type yes in the chat box so that I can understand you have understood. Okay. Yes, thank you so much, Bas. And coming to the next reaction, 3O2 giving 2O3. For this reaction at 298 Kelvin, Kc is given. It is 3 into 10 to the power minus 59. If the concentration of oxygen at equilibrium is 0.040 molar, then the concentration of O3 in molar term, that is in molarity form, is. So basically we have to find out the concentration of O3. We have to find out, this is the concentration of O3. This is what we have to find out. So we have this reaction 3O2 equilibrium with 2O3. O2 is oxygen and O3 is ozone, right? So if I have to write, I have to do, it is product by reactant raised to the stoichiometric coefficient. The product is O3. So write its concentration and the power is 2. And the reactant is O2. Write its concentration and its stoichiometric coefficient is 3. Okay. Now what is O3 square? Take this term to the other side. So we will get Kc into O2 cube, right? Take this to the other side. You will get this relation. Now substitute the values. So Kc is 3 into 10 to the power minus 59 into, what is the concentration of oxygen? The concentration of O2 at equilibrium is 0.04 power 3. Now if we solve all these things, we will get 19 into 10 to the power minus 64 as the value for concentration of O3 square. But we need to find out only the concentration of O3, not its square. So what I have to do? Just take the root of this equation of the value. Take the root value. So O3 will be equal to the root of 19 into 10 power minus 64. If I take this minus 64 from the root, I will get minus 32, right? Minus 32 I will get. And if I take this 19 out for 16, if for root 16 is 4, right? Then for root 19, it will be more than 4. It will be like a 4 point something. So in the given option, we have only one option which is having 4 point value, that is option A. So we have 4.38 into 10 to the power minus 32. Option A is the correct answer. Option A is the correct answer. That is the concentration of ozone. Clear? Clear for all? Okay. Now coming to the next question, the equilibrium constant for the following reactions are given. For the first reaction, it is K1. For the second reaction, it is K2. And for the third reaction, it is K3. Now we have to find out the equilibrium constant for this given reaction. So how to get the desired reaction from the given 3 equation? So here in this desired equation, we have NH3 and O2 in the reactant side. But from this reaction, we have NH3 only in the first equation, but that is in the product side. Just you reverse the reaction. So let me reverse this first equation. So I will get 2NH3 giving N2 plus 3H2. So if we reverse the reaction, what we have to do? We have to take the inverse, right? So the equilibrium constant will be 1 by K1 for this reaction. I have to take the inverse. Then O2 is at the reactant part only. So there is no change in the second reaction. Just write as it is. It will be K2 only. And what else we have? We have 3 moles of water. We have 3 moles of water in the right side. But in the third reaction, we have water, but there is only 1 mole. So what we can do? We can multiply this third equation by 3. So if I multiply this third equation by 3, what I will get? I will get 3H2 plus 3 by 2 O2 in equilibrium with 3H2O. So if I multiply a reaction by a number n, what I have to do? That has to go to the power. Since I have multiplied this by 3, it is K3 power 3. Okay. Now what we can do? We can add all the 3 equations. By adding all the equations, we get, what we get? We get this desired equation, and the K value for this is, just add everything. If I'm going to add everything, I have to multiply the constant. That is what we have studied under the properties of equilibrium constant, right? If I'm adding 2 equations, then I have to multiply the equilibrium constant. I have to multiply the equilibrium constant. Now I am going to add all the 3. If I add all these 3, I will get this equation. If I add all these 3, I will get this equation. Okay. So I will have 1 by K1 into K2 into K3 cube. Okay. So what is this? It is K2 into K3 power cube by K1, right? So it is given in option. So this is nothing but the equilibrium constant for the given reaction. Yeah, it is given in option A. It is given in option A. Okay. Fine. Now let's try to solve one more question. One JEE question we will solve. 4.5 moles each of hydrogen and iodine is heated in a sealed 10-liter vessel. At equilibrium, 3 moles of hydrogen iodide were found. The equilibrium constant for the given reaction is. Okay. So there is no option because it is a JEE question. We have 10 numericals in JEE, right? With no option. So this is one among it. And the given equation is H2 plus I2 giving 2HL. So this is the reaction. Now at time t is equal to 0, initially we would have only the reactant. And we have 4.5 moles of hydrogen and iodine. We have 4.5 moles of the each reactant in the initially, and there is no formation of the product. So it is 0. Now, after some time t, or I can say at equilibrium concentration, at equilibrium point, 3 moles of hydrogen iodide were found. Equilibrium means reactant and product both are in the same value, right? If the hydrogen iodide concentration is, if the number of moles of Hi is 3, then obviously H2 and I2 will also be 3. This is the equilibrium thing. Now, if I have to write the Kc for this reaction, how I have to write? Product concentration raised to the stoichiometric coefficient by reactant concentration. By reactant concentration, stoichiometric coefficient is 1. So just put 1. Okay. Now, substitute the concentration values. So these are the equilibrium concentration values. So for hydrogen iodide, it is 3. So I have to put 3 square divided by, for hydrogen it is 3, and for iodine also it is 3. So 3 square is 9. 3 into 3 is again 9. So it is equal to 1. So the Kc for the given reaction is, equilibrium constant Kc for the given reaction is 1. Equilibrium constant for the given reaction is 1. Okay. I hope this question is clear to all of you. If you're having any doubt, just ask me. We will solve one more question. Shall I move on to the next question? Do any of you have any doubt? We will look one more question for today's session and then we will wind up the class. Shall I move on to the next question? Yes or no? Okay. Thank you, Suresh. Thank you so much for your response. Yeah. Coming to this question, for this reaction, sulfur dioxide reacting with oxygen to give sulfur trioxide, Kp is given at 27 degrees Celsius and at 1 atmospheric pressure. We have to find out the Kc for the same reaction. So we know the relationship between Kp and Kc, right? Kp is equal to Kc into RT power delta Ng. So what is delta Ng? Delta Ng is equal to number of moles of the gaseous product is, it is 1. And for the reactant, we have 1 plus half. What is 1 plus half? It is 3 by 2, right? So I have to subtract 1 minus 3 by 2. It will be equal to minus 1 by 2. So in place of delta Ng, substitute minus 1 by 2, and Kp is given in the question. Substitute Kp is 2 into 10 to the power 12, which is equal to Kc. R value is also given. So 0.082 into temperature is also there. Temperature is 27 degrees Celsius. We have to substitute the temperature in terms of Kelvin. So convert this to Kelvin. Add to 73. You will get 300 Kelvin power minus 1 by 2. Okay. Now on solving this, we will get 9.92 into 10 to the power 12. But we have to give the value in terms of 10 to the power 13. So just Kc is equal to 0.992 into 10 to the power 13. And also we have to give the value in the nearest integer form. Nearest integer is nothing but, what is the nearest integer for 0.9? It is 1, right? 1 is the nearest integer. So this is the K value. So the answer here is 1. 1 into 10 to the power 30. Okay. So with this, I will end the today's session. I hope the session is very useful and clear to all of you. So try to come to the class on time from next session onwards, from tomorrow onwards. Okay. So that you will not miss any of the topics. Okay. If you're having any doubts, you can ask me. And oh, sorry. The ID is in the name Suresh, right? So that's why I have called you Suresh. Okay, Reena. If you're having any doubt, you can bring those doubts to me in the next class, or you can ask in today's class also. I will give you some seconds. You can ask. Okay. So no doubt for today. Okay, then thank you so much for listening the lecture. Meet you all. Meet you in the next class. Thank you. Take care. Bye-bye.